let's imagine again this kind of water tower situation. Right? It's a house. I'm a wonderful artist. But so here you have your water coming in from the tap. And you are controlling that. So if my job is to do level control over here, remember, this is something that absolutely is true, that high tower level needs to be kept constant. But they cannot manipulate. So if you kind of think of the classic manipulation for the level control problem, right? You always think of manipulating the outgoing stream. But in this particular case, it would be silly to manipulate the outgoing stream, because then everybody else, because the level went down a bit, like your taps would stop running. That doesn't make sense, right? So what do they do instead? That level controller is changing. So this is the outgoing stream, right? The level controller is changing here the amount of water that goes into the tank in order to keep the tank level constant. And maybe that's coming from wherever the water is coming from the river or whatever. They've probably got a big pump over here that's pumping all that water up that hill, but they pump at some non-constant rate in order to keep the level constant. So what's the difference between that and our steam boiler example, right? So the steam boiler example looks something like this. Here we've got steam going out, and we've got some source of energy, and we've got some makeup water. And so if we think about what the controlled variables are here, it's very likely that this system is trying to control a pressure in the boiler. It's trying to deliver some consistent pressure of steam or quality of steam, right? And it also wants to control the level of the water in the boiler, so that whatever the thing is that we're using to boil the water, whether that's maybe a coil, an electrical coil, or some kind of an arc or whatever, so that that doesn't boil dry. So just like a kettle, right? Like if you were operating your kettle in a mode where you're actually trying to produce steam from it, right? We know that we don't want our kettle to boil dry. But so those are the controlled variables. And I think the flaw in a lot of people's reasoning about this is that even though we've been doing dynamics for so long, your first encounter with problems like this was in CIR subjects where you had a very ingrained assumption of steady state. And so I think for many of you, it is impossible to imagine that adding more energy will not immediately produce more steam. I mean, will not produce more steam over here, right? It is true that if I add energy over here, there will immediately be more boiling. It is not true that there will immediately be more steam coming out of the boiler. And the difference between this boiling, the energy going in, and the steam going out is explained by the dynamic mass balance around that boiler volume. If you ignore it, none of the stuff that they say makes any kind of sense at all. If you ignore the dynamics of the system, when you read through the chapter, it's like they're just talking about this weird situation and you can't get your mind around it. It's like, oh, well, if the steam gets more, then I'll have to put more energy in. It's like, no, You have to put more energy to get more steam, silly, right? It doesn't work that way, but it's because you're thinking about the causality wrong. You can withdraw steam without boiling anymore. In fact, I can turn that boiler off. It will still be full of high pressure steam at that moment in time. And if I then open the valve that goes out of that boiler, more steam will come out than in the previous times where the valve was closed. This is just absolutely true, if you think about it dynamically. But if you imagine, and this, where do you get this idea? You get this idea from ignoring the dynamics in all of the heat exchanger problems and all of the phase transfer or phase change problems that you did in CIR and and CIO. If you allow yourself to say flow out equals Q times whatever factor, Q times lambda. If you have that equation in your head, nothing here makes sense. And especially if you imagine that it goes something like this. If you actually imagine that equation looks like this, let's say Q is equal to lambda times S, right? Let's say that's like the most simple version of this. If you imagine that everything's at equilibrium and I'm putting in some amount of energy and lambda is the heat of evaporation of the steam, you probably have written an equation like that somewhere. Okay? And now you're being tricked twice by your brain because you're writing it like that and you've become hopefully a little bit used to us writing these equations in causal form. In other words, you're imagining that it's the steam that is causing the Q, or like you're calculating Q from the steam flow rate. But I think a lot of you are like also reading that and saying, oh, that means like more steam means more Q. And so that's the key idea, right? As soon as you break that, because that is wrong in the dynamic case. Right? What is true is that when I add more energy, more steam will enter into that volume. And if all the downstream people are still using steam at exactly the same rate, this stream will not increase when I increase Q. What will happen instead is the pressure inside of the boiler will go up. Why? Because I'm adding energy, so I'm boiling, right? Phase change is happening. The boiler volume is fixed. If there's more enthalpy in that boiler, which means there's more gas and less liquid, the total volume or the total gas volume is roughly the same, but there's more gas molecules. And so the pressure goes up. There you go. Another way of kind of solving this problem is imagine that, another easy way of understanding this is imagine that this steam was zero. In other words, I imagine that I had closed the downstream valve. Then it's obvious, right? Like then it's obvious that if I close the downstream valve, obviously then if I add more energy, there's a space between nothing happens and the boiler explodes, which during that time the pressure just ramps up. But if the valve isn't fully closed, the pressure can ramp up. And remember, we're imagining, and like this is why I think it's useful to have that little man there. You have to be imagining that this boiler is servicing a whole lot of different users that are all, they are not just setting their valves at fixed positions so that when the pressure goes up, they just get more flow. No, they are trying to get a certain amount of flow. So if the pressure goes up and they get a little bit more flow, they'll close their valves. Right? Just like you would. If you're pouring yourself, okay, bath is maybe not a good example, but let's say you're in the shower and you've got your stuff just exactly where you want it. And suddenly, like, there's a drop or an increase in pressure. Typically, let's imagine like an undesirable situation, suddenly the pressure drops. What do? Do you just say, the pressure's dropped? No, like you reach out for the tap and you open it up because you want like a certain amount of flow. Right? And so that's where the puzzle is. I think for a lot of people, that's what they really struggle with when they read through the boiler example, is just understanding the causality. I like this example because of this, because it breaks this thing that I've spoken of before. It breaks the link between the physical flow of material and the flow of information. It happens too frequently that we look at the arrows that are on the pipes to understand how information travels through a unit, especially in the case of gas. But as you see here, even in the case of liquids in this Hightower example, information can flow the other way. In other words, the downstream people can be making decisions on my behalf. That happens. Now, we'll be coming back to this basic idea of who makes the decisions, and I think it's just worth placing a little bookmark in your brain here that somehow, for whatever reason, it's easier to understand wild streams being upstream than wild streams being downstream. It's easier to understand that the inputs into my system could be anything than to understand that the outputs from my system could be anything because the downstream people can be moving their valves. We'll get back to this because it forms like a key choice in control philosophy, whether we design to accept disturbances from upstream and control ourselves, or whether we design to accept disturbances from downstream.